Can you hear me? Can you hear me in the back? Yeah, so maybe let's start without the microphone. So I will start just with some wrap up from last time. Just remind you what we did. So I basically introduced objects called Poisson Lie groups. So these were just Lie groups with Poisson structures that, with the Poisson structure that was compatible with the group operation in the sense that the multiplication map is a Poisson map. Okay.
Vai colocar de volta aí, em volta do pescoço se foca. Tá ligado já.
How was this again?
Aqui, ó, a camisa. Bolso.
Okay. Okay, and then the second object, I think this is too loud, isn't it? It's okay. So the second object that we discussed was a Lie groupoid. So the notation was something like this. So this was basically a group-like object, so it was basically a manifold with a partially defined multiplication with certain properties, and we gave some examples. And then we spoke a bit about how to couple the groupoids and symplectic structures. They're symplectic groupoids. So here the compatibility condition between the symplectic form and the groupoid operation was that the graph of the multiplication was a Lagrangian submanifold of the triple product of the Lie groupoid. And just to remind you how this was related to Poisson structures, so out of this, out of a symplectic structure compatible with the groupoid structure, so this is, again, my notation is just like here, the base is M. We saw that in the case of a symplectic groupoid, we saw that M, the base, inherits Poisson structure, uniquely determined by the fact that the target, so this is the target map, is a Poisson map. In which case the source will be an anti-Poisson map because the inversion is anti-symplectomorphism of the groupoid. Right? So in particular, any symplectic groupoid induces a Poisson structure on the base for which the groupoid itself is a symplectic realization in the sense of what Rui has been talking about. Right? So a couple of remarks, immediate remarks about the relationship between the groupoid and the symplectic structure on the base. So the first remark is that, as I told you in general, so let's remember just something here. So I told you that groupoids always have orbits, right, in general. So in the case of a symplectic groupoid, the orbits are just the symplectic leaves of the Poisson manifold. And the other observation is that I also told you that groupoids, the other key ingredient of a groupoid was that it had isotropy subgroups. So these were all the arrows that that begin and end at the same point. And in this case, basically. So this, in the case of a symplectic groupoid, this is so these are Lie groups, and they integrate the Lie algebra structure on the conormal bundle of symplectic leaves. So just a word about that. I think Rui didn't say that explicitly, but so it turns out that on any Poisson manifold, if you look at a point, right, and you look at the symplectic leaf there, and you look at the dual, at the conormal bundle of the tangent space of the symplectic leaf, then this naturally inherits a Lie algebra structure. So this is basically the linearization, the dual of the linearization of the Poisson structure on the transversal direction that Rui spoke about. So you can linearize that. And so the symplectic groupoid also sees that, and in fact offers Lie groups that integrate that Lie algebra at each point. Okay, so these are two ways in which you can see that the symplectic groupoid kind of integrates the Poisson manifold. So it gives orbits that integrate the distribution given by Hamiltonian vector fields, and it also integrates the Lie algebras in the transversal direction. So let me just give you some initial examples of symplectic groupoids. I guess I didn't talk about them last time. So just very basic examples. So the first one is if M is a symplectic manifold, so in particular, if it's a symplectic manifold, so there are two symplectic groupoids that you can create from it. So one is just the pair groupoid with a symplectic structure given by the product, except that you change the sign of the second one here. And you can do the same also, so this is a groupoid over M. You can also take the fundamental groupoid that I also spoke about, and this will be also a symplectic groupoid over M. And in this case, the Poisson structure induced on the base is just the original symplectic form here. Another example that is kind of, it's simple, but it will play a role, is if you take any manifold whatsoever, and if you see it, basically, let me say it this way. So if you take any manifold, and you look at its cotangent bundle, right? So you can see a cotangent bundle, or in fact any vector bundle whatsoever over a manifold as a groupoid. And the way you do it is that in this case, the source and target are the same, and they are just the vector bundle projection. And the groupoid operation is just the fiber-wise addition that you have on a vector bundle. So any vector bundle can be seen is a Lie groupoid in this way. Okay, so in particular, this guy. And this is a symplectic groupoid with respect to the canonical symplectic form, and the induced Poisson structure here is just 0. And then finally, if you have a Lie group, then you can look at its cotangent bundle, and we saw that the cotangent bundle of a Lie group is naturally a groupoid. So first of all, it is a symplectic manifold because it's a cotangent bundle, but it's also a groupoid over the dual of the Lie algebra, just because it has the structure of an action groupoid. So remember that, as a manifold, this is just G times G star. You can trivialize it. But because, in any G manifold, was associated naturally with a groupoid called the action groupoid, and because G acts on G star by the coadjoint action, you can put these things together into a groupoid, and this is a symplectic groupoid as well. Okay? Notice that also, just a remark, that from the previous example, this is also a symplectic groupoid in this kind of, more silly way over G. So the cotangent bundle of a Lie group is in fact a symplectic groupoid in two different ways. And this is what is called a double symplectic groupoid, and these things also appear, particularly related to Poissonian groups. And then one of the problems that I remarked here before was, I'll just call it this integration problem. At least one version, first version. So this is about if you're given a Poisson manifold, if there exists a symplectic groupoid such that the target is a Poisson map, okay? Just so that this given Poisson structure here is the one induced by the symplectic groupoid. So this turns out to be not true in general, but I will discuss more that in a bit. So this was what I would like to have said last time. And the other thing that I did not mention, that I should have mentioned last time, was the notion of Poisson groupoid, which is just another, it's something that also belongs to this list of initial examples of multiplicative structures, which is basically a way to unify these two. So just give a definition. So here we are still in the 80s, right? So I said that I would follow the historical evolution of these ideas. So this is early 80s, this is more or less mid 80s, and this is late 80s. So what is a Poisson groupoid? So here the setup for this notion is, again, you have a Lie groupoid, and you have now a Poisson structure and we'll say that this pi is multiplicative if it's again a condition in terms of the graph, just like for symplectic groupoids in which the graph had to be Lagrangian, but now the graph, so this inside G cross G bar, where again I'm switching the sign of the Poisson structure here. This is coisotropic. I'll remind you what that means. And in this case, the pair is a Poisson groupoid. So this is also a notion that goes back to Alan Weinstein. So let me just make a couple of remarks about that. So first, what coisotropic means, since it was never defined here. So you probably all know what coisotropic submanifold of a symplectic manifold is. So it's just a generalization of that. So here, so recall that if you have a Poisson manifold, and if you have a submanifold, the submanifold is called coisotropic. If when you map, it's annihilator. So this is the annihilator of the tangent bundle of the submanifold. So when you map it using the tensor, so any Poisson structure gives rise to a map like this. So this lies on TC. Okay, so, or another way to say it is that equivalently, if you have any function, let's say that is 0, along the submanifold, and you look at its Hamiltonian vector field, so the Hamiltonian vector field is tangent to the submanifold, so it's equivalent to that. And then a simple exercise that illustrates the importance of this concept in Poisson geometry is that, so if F is a map between Poisson manifolds, so this is a Poisson map if and only if the graph of this map, so this is just the points of the form, is coisotropic in M1 cross M2 bar, changing the sign of the second. So from this exercise, you clearly see that Poisson Lie groups are examples of Poisson groupoids, because the definition there was that the multiplication map was a Poisson map, but then the graph has to be a coisotropic submanifold, and that's what I'm saying here. Just notice again that, here you would have the trouble of saying something about the multiplication as a map, just because, just like for symplectic groupoids, the multiplication is not defined on the product of G with itself, but just on the composable pairs. And the composable pairs they don't have any geometrical structure in principle. Right? Just G times G is a Poisson manifold, but the submanifold you don't know. So the way around it is that you formulate something in terms of the graph. Right? But then for the case of Poisson Lie groups, you actually have a map, and then this just becomes the original definition. And another, if you want, an exercise is to check that symplectic groupoids are also examples. And this is very similar to the exercise that I proposed yesterday about characterizing symplectic groupoids by this formula for the 2 form. There's something that, somehow for a symplectic, for a non-degenerate 2 form on a groupoid, the dimension of the base is kind of predetermined. So saying that it's coisotropic will imply that it's Lagrangian. So we can check that. There are general properties of Poisson groupoids which are similar to those of symplectic groupoids. For example, the identity, so the embedding of the identities inside the groupoid is coisotropic. In the symplectic case, it was Lagrangian. And you have that, if you pull back functions from the base to the groupoid using source and target, they Poisson commute. And the inversion of the groupoid is anti-Poisson. There are several properties that you can derive in this context. And there are other examples, but mostly, rather than going in that direction, what I'm going to start discussing now is how to describe all these objects infinitesimally in terms of Lie algebra, or Lie algebroids that will appear as infinitesimal structures for Lie groupoids. How do you express them in infinitesimal terms? Okay, so let me start. So I'll follow here the same order. So I'll start talking about infinitesimal structures one by one. First for Poisson Lie groups. So then I'll tell you what the infinitesimal of a groupoid is, of a symplectic groupoid is, and what a Poisson groupoid is. Right, so let me just remind you very quickly So that's the outline of these lectures. So I'll talk about the infinitesimal of Poisson Lie groups, which are called bialgebroids, and then Lie algebroids, which are the infinitesimal of Lie groupoids, and so on. Right. So just before I start talking about Poisson Lie groups at infinitesimal level, let me just remind you a couple of things, because I'll be using them, which are like different ways to look at the Lie algebra. So first of all, you can extend the Lie bracket to, exterior powers of the Lie algebra. This is called like a Gersten-Haber kind of bracket. And no, because it satisfies a Leibniz identity, it's basically equivalent. It's really equivalent to just saying what the Lie bracket is. You can dualize the bracket and encode it as a differential on the exterior powers of the dual of the Lie algebra, right? That's the Chevalier-Allenberg operator. And there is yet another way, which is to look at the dual. Maybe I should do this. Oh, no. It was already. So you can also dualize and go to the dual of the Lie algebra, and there you have a linear Poisson structure that is also equivalent, like knowing that is also equivalent to knowing the Lie bracket on G.
So what are the conditions you need to impose on the Gersten-Haber bracket so as it would come from a Lie bracket?
Right, well, so...
Some degree condition? Or?
Yeah, so it has to have a -1 degree, satisfy Leibniz with appropriate sign, and the graded Jacobi...
Yeah, no, okay, these are the properties of Gersten-Haber, so just any Gersten-Haber
yeah.
over
Right,
degree
yeah.
-1.
Right, because the graded Jacobi identity will just reduce to the usual Jacobi identity in degree 1. And if you know it in degree 1 and you extend it using Leibniz, you get the graded Jacobi. Right. So these are like 3 points of view. So we'll be kind of using this
And of course, the differential is also equivalent. The differential is
right.
Degree, which is what, co-derivation or derivation?
Yeah. So it has to be a derivation. Yeah, derivation with the appropriate sign. Yeah, exactly. So these are all really equivalent points of view. And okay, so I don't want to get there yet. So let me then go back to Poisson Lie groups and tell you one way to get their infinitesimal description. Okay, so let's consider Poisson Lie group. And let's recall a property that I left as an exercise to be checked, which is the fact that whenever you take the derivative of a multiplicative bivector field or even multivector field by something that is right invariant, the result is right invariant. So this is right invariant if x is right invariant. And from that, you see that you can define the following. So this defines the following operation in a natural way. So basically you can find a certain operator from here to here just by the following condition, that if you start with the Lie algebra element U and you take the associated right invariant vector field and you differentiate the bivector in that direction, this is something that is right invariant. It's a right invariant bivector field, and therefore is determined by something here. Okay? And there are a couple of observations at this point. So you get this operator just by this property. So observations, which are really not complicated to check. The first one is that, so you could have done this for any multiplicative bivector field, but one property is that if the bivector field is Poisson and satisfies this property, then this guy squares to 0. And what do I mean by square to 0 if it's only defined here? You extend it in the usual way using Leibniz for the higher powers. Okay, with signs always. So I won't get into all the signs. Okay, so that's the first condition. And therefore, by one of the characterizations there, by the second one, this gives me a Lie bracket on G star. So remember, so whenever you have this differential on the dual, this is the same as a Lie bracket on the space. So here you have a differential on exterior powers of G, therefore you get a Lie bracket on G star. Right, so that's one thing. And the other thing is a very important condition that you can also read off from this equation pretty easily, which is the fact that the following is satisfied. So if you take D of the Lie bracket of two elements, this is du of V plus U dV. And how do you see that right away? Basically what you do is, you can just put a U bracket V in here, and you put a U bracket V in here, you expand this out. Remember that right invariant vector fields preserve the, well, for me the Lie algebra bracket is given by right invariant vector fields for some reason. So then you just get this equation right away. Okay, and so anyway, so you get this Lie bracket on G star satisfying a certain property. I mean, so that its Chevalier-Eilenberg operator preserves the bracket on the dual. That's the point. And and this Lie bracket is just in some. Remember that I also told you that over the identity, this Poisson structure had to be 0. And by what I said before, this induces, just by general Poisson geometry, this induces a Lie algebra structure on the dual of that tangent space, which is the conormal bundle of the point. And that's the same thing. That's this.
So the cohomology of this complex is going to be
It's the Lie algebra cohomology.
well, like that of Louis introduces the Poisson cohomology of its delta.
Yeah, so this is it's different. No, it's not the same.
The delta uses the Poisson structure.
Right. Yeah. Well, it's yeah. I mean,
Poisson cohomology that.
well, no, it's different.
Oh, it is.
Yeah. But I mean, well, maybe I'll say a word about that. And in any case, and this gives me, I guess, the definition that I'm looking for.
The dual mathematical being the dual of the Lie algebra is still a different homology.
Sorry? Yeah, I think it is. Yeah. Okay, so the definition of a Lie bialgebra is that you have a pair given by a vector space and its dual, and suppose that they are both Lie algebras. So this is a Lie bialgebra if that compatibility condition is satisfied. So if you take the operator associated with the Lie bracket on G star, this is a derivation of the Lie bracket on G. this fell again. I'll just leave it like this for now. Okay, so that's the definition of a Lie bialgebra, and then I can state, right? So it's kind of simple to see how you get a Lie bialgebra from a Poisson Lie group. Then usually, going back and and checking that this is all you need to know is the more complicated part. It's always like integrating is always more difficult. But so here's a theorem, right? Goes back, I think. I don't know if first primitive maybe Dreamfield or. Okay, so that's the theorem. Is that at least for simply connected Lie groups, there's really a correspondence, a one-to-one correspondence between multiplicative Poisson structures and Lie bialgebra structures. So you encode the multiplicative Poisson structure at the Lie algebra level as a Lie algebra structure on the dual that is compatible with the Lie algebra structure we had before. Okay, so that's the content of this theorem. And explicitly, in one way, is just this operation that I explained here. Right? So basically, that's how you derive from the bivector the map that you need to describe it infinitesimally. So you see, but one nice thing about having the infinitesimal description is that it may be easier for you to even find examples or study the global object. Right? So let me start filling this table here. So this guy is equivalent to Lie bialgebra. But in any case, how do you find Lie bialgebras around? Right? I mean, how do you recognize that you have Lie bialgebras? So it turns out there's a very nice way to do that. There's a different point of view. Even like from the definition, the way I stated it, it's not even clear. It's not totally immediate that if I swap the roles of G and G star, that this definition is symmetric. Right? Because I'm just saying that, the operator of the bracket here is a derivation of this one, of the bracket here. But, in principle, we don't know that the other way around works. So this is a more symmetric way of looking at Lie bialgebras that turns out to be very important. So one thing that you could do is, because you have Lie algebra structures on G and G star, so suppose that you just have a pair of Lie algebras so that the vector spaces are in duality, right? So you can take their direct sum, and this direct sum will have naturally a symmetric pairing which just comes from pairing G and G star, right? And then, what you do is that you can write a bracket there on this direct sum that restricts to the Lie bracket on G, restricts to the Lie bracket on G star, and has the additional property of being ad-invariant. Okay? And this completely determines this bracket. There's only one formula you can write with these properties. Okay? And then the amazing fact is that this extra compatibility condition, that was the only thing missing, turns out to be equivalent to this formula satisfying the Jacobi identity. Okay, so basically you get a Lie algebra on the direct sum of G and G star by a specific formula. And this really, is a more, a more symmetric way to understand this, particularly because there is this associated notion of Munning triples. So basically, a Munning triple, axiomatizes this object here. So basically, what you have is a triple of the algebras, such that D, the first one that I write there, is the direct sum of, as a vector space, is a direct sum of G1 and G2. This D has a net invariant, non-degenerate, symmetric kind of inner product, scalar product, and G1 and G2 lie in there as isotropic Lie subalgebras. So they are closed under the bracket, and the pairing vanishes on them. Right? This is exactly the situation that we had here. But it turns out, because of the uniqueness of this bracket, upon restriction to G star and adding variance, you actually get an equivalence between Lie bialgebras and Manning triples. So the way to find Lie bialgebras is really by finding Lie algebras with adding variant inner product and seeing if you can split this thing into direct sum. That's like a natural way. Maybe I'll just write here Lie bialgebra, but I could also have written here Manning triple. So that's the infinitesimal story. And why does it help you? I mean, there are some immediate consequences of this fact. One is that the symmetry between G and G star is manifest, right? I mean, with the definition of a Manning triple. And therefore, you immediately see that, basically, if you integrate by the theorem by the correspondence between Poisson Lie groups and Lie bialgebras, that if you find the Poisson Lie group, then there's a pair. I mean, they come in pairs. One integrates G, the other one integrates G star. Right? So they come in kind of dual pairs over there. Dual. You have the Poisson Lie group, and you always have its dual, right? So this one integrates G, and this one integrates G star. So a very simple. The first example of this story here is if you take here the Poisson Lie group where the Poisson structure is 0, then its dual Poisson Lie group is just the dual of the Lie algebra with the linear Poisson structure. But there are much more interesting examples. So, for example, here is there's a natural way that you can split SL and C as a direct sum, and you have a scalar product there, which comes from taking the imaginary part of the trace, and this makes this triple SLNC, SUN, and SBNC into a Manning triple, and this is a way to see that SUN inherits a natural Poisson Lie group structure, and the dual group you can also identify. And this is one example of this Iwasawa decomposition. Just a particular case. But anyway, so that's what I wanted to tell you about Lie bialgebras. So, you can find many examples of Poisson Lie groups by finding Lie bialgebras around. Alright, so let's move on now to the infinitesimal description of Lie groupoids. How are you doing with time? So I think the experiment yesterday was reasonably successful. So I'll again ask you to ask your neighbors if they know what a Lie algebroid is, and if they do, if they can explain that to you. And I'll give you a couple of minutes to do that. So I'll tell you now. perhaps you know already, so let me just repeat then to you what a Lie algebroid is. So basically, a Lie algebroid is given by three main ingredients. So you have a vector bundle. So just like Lie groupoids were Lie groups that are kind of spread over a manifold, right? I mean, Lie algebroids have the same idea. So they are kind of like Lie algebras in a way, but they are also spread over a manifold. So the first ingredient is a vector bundle. Oops, no, that's not what I want to do. And the second one is a bundle map from the vector bundle to the tangent bundle of the manifold. And then you have a Lie bracket on sections of this vector bundle. And there is a compatibility condition between the Lie bracket and this map, this bundle map, called the anchor, given by the Leibniz identity. So this really kind of, is very similar to the relationship to what the Lie bracket, the vector field, satisfies. It's just a generalization of that. Okay, so the main examples, on the one hand, are the tangent bundle of any manifold, in which case this bundle map is the identity map, and the bracket on sections of Tm, which are just vector fields, is just the usual Lie brackets of vector fields. Right? And then the other extreme is if you take this base manifold to be a point, in which case, the compatibility condition is vacuous and you just get a Lie algebra. So these are the two extreme cases to have in mind. And about the first one, you can even get something a bit more general. For example, if you take any involutive subbundle of Tm, this will still be a Lie algebroid. Right? As long as it's closed under the Lie bracket. So regular foliations are Lie algebroids, or the tangent to that. Right? And just as, group actions gave rise to Lie groupoids, infinitesimal actions of Lie algebras also, analogously give rise to Lie algebroids. And it's kind of simple to see what the algebroid structure is. So in this example, this anchor map is nothing but the action itself, which you can view as something like this. So this is something that for a Lie algebra element in a point gives you the vector field, generating vector field of the action evaluated at that point. Right? And the bundle here is just a trivial bundle. And so another example that is a key example to us already. No, that's right. Now already came up in Ruth's talk this morning, even though he didn't bother to say the name of the object. It's just if you have a Poisson manifold. So there's a very natural Lie algebroid associated with it, and the ingredients are, as vector bundle, you take the cotangent bundle of the manifold. As anchor map, you just take this natural bundle map associated with any Poisson structure. Basically the map that takes, the differential of a function to the corresponding Hamiltonian vector field. And the bracket, so it suffices if I tell you the bracket on by the Leibniz rule on differentials like this, and this is just, he gave the intrinsic formula, but it suffices to know this. Just like here, I never told you the bracket, but the bracket is the unique bracket. So what are the sections in this first example? The sections here are just functions on M with values in the Lie algebra. So the constant functions are just Lie algebra elements. And there is only one bracket on these functions that restricts to the known, to the original bracket on constant functions, on the Lie bracket on G, and the Leibniz identity. There's just one bracket that you can write with these properties here. Okay, so that's a Poisson. That's the Lie algebroid of a Poisson manifold, right? So there's something general about Lie algebroid that maybe I should mention. So a general property is that, now this is for the algebroids, is that if you take this anchor map right? There are two things you could look at. First, you could look at the image of the anchor map in Tm. So this really gives you a subspace of Tm at each point. So it's a distribution, and of course it's not just a subbundle. The dimension, the rank of this image here can vary from point to point, but it's one of these generalized distributions, and it's always integrable. So there are always leaves that may vary dimension as well, but there are always leaves associated with it. Right? So the leaves are called the orbits of the Lie algebroid. But this is always integrable distribution. And the other object you could look at is the kernel of this map. And it turns out that at each point of M, this is a Lie algebra. But just the kernel. It's not true. This is something that people get confused about sometimes. It's not true that a Lie algebroid, if you just pick a point and you look at at A over that point, that this is a Lie algebra, right? I mean, this would be the case if you could take the function out. But because you have the Leibniz rule, it's not true that this Lie bracket localizes over fibers on fibers. Right? But it does if you are on the kernel of this map. So that's where this Lie algebra structure is coming from. So again, in the case of a Poisson manifold, right? So this map was just the map associated with the Poisson tensor. So this distribution is just the distribution spanned by Hamiltonian vector fields at each point, and the leaves are just the symplectic leaves. Right? And these Lie algebras are exactly the Lie algebras I spoke about before, coming from the linearization on transversal directions to the symplectic leaves. Okay, so there's one more thing I should say about Lie algebroids, which is how you get Lie algebroids from groupoids. Okay. So remember, let me try to draw a picture for what's going on. So this is M, the base of the groupoid, and I think I represented before. You have S fibers, and then you have T fibers. Right? And what you do now is first you take A to be the kernel, so basically the tangent space to S fibers at the units. So basically, you take the S fibers, and here you take the tangent spaces at each point here. So this gives you a vector bundle, that's A, right? And then you use the target map as the anchor. So the anchor will be the differential of the target restricted to A from A to Tm. Right? So this is the map. It goes like this. And to get the Lie bracket on sections, so now I need a bracket on sections of the Lie algebroid. Then, what is a section of the Lie algebroid now? It's just, taking vectors which are on these tangent spaces here. And what you can do now is do exactly what you do for Lie groups. You can translate them, right? And get vector fields over the groupoid. So, remember that left and right translations are defined on groupoids, except that you have to be a little careful about, this composition issue, right? So, for example, you can bring this guy over to this point by right multiplication. So this guy goes here. And this guy, you can bring it here, or here, and this guy comes here. So in the end, if you have a section, and you translate, like right translation kind of, is something that slides over this fiber here. So you can just push the section and cook up a vector field. And just like for Lie groups, the right invariant vector fields are closed under the Lie bracket. Right? So you do this by identifying this with the right invariant vector fields. And the reason why I chose right invariant, many people choose right invariant just because it's better to compose things like this. You don't have to think about it. But then formulas get a little messed up with signs in the end. Anyway, so let me summarize what we have so far. So, we have Lie bialgebras. Now we have here Lie algebroids, except that maybe I should tell you exactly what is the theorem, or if there is a theorem relating these two concepts, right? So it turns out that there is versions of this Lie theorems that we all know for Lie algebras and Lie groups to the framework of Lie groupoids and Lie algebroids, except that the theorem that says that for any Lie algebra you can find a Lie group does not hold here. So not every Lie algebroid can be realized as the Lie algebroid of a Lie groupoid. This is not true in general. Okay? And the obstructions, for this problem were studied by Rui and Marius. And, but the other theorems hold. So, for example, if you have, I didn't say what morphisms of groupoids and algebroids were, but, you can probably guess what they are. And, so, for example, you can integrate morphisms. So, first of all, the first theorem says that if you have the Lie algebroid of a Lie groupoid, then you can replace this Lie groupoid by a source simply connected one with the same Lie algebroid. Right? So the theorems that hold for simply connected Lie groups in Lie theory, for groupoids have to be source simply connected. Right? So this holds. So if there is an integration, there is a source simply connected integration. Morphisms, as long as the Lie groupoid on the target of a morphism, right, is source simply connected, then you can lift an infinitesimal morphism to a global morphism, just like for Lie groups, if you have the groupoids around. And then the theorem that Lie algebroids can be integrated to Lie groupoids is not true in general. So I may say more about that later. Right. So now I would like to just say a few words about just going down here my list just to explain how you complete the table. One more step. So maybe I should say just remark that just for Lie algebras, you also have these 3 points of view to Lie algebroids, exactly the same, totally analogous. So you can extend the Lie bracket on sections of A of a Lie algebroid to sections of exterior powers, and this you do that so that it's a Gersten-Haber bracket. You also have, if you dualize, you get a differential on exterior powers of the dual of the vector bundle. So these are the formulas relating the differential and the bracket and the anchor, right? The first formula there gives the anchor in terms of the differential in degree 0, and the second formula gives the bracket in terms of the differential in degree 1, and that's all you have to know. And you also have a linear Poisson structure on the dual of any Lie algebroid, and these are the relation, the conditions, the defining conditions for this Poisson structure. So in some sense, a Poisson manifold is a particular case of a Lie algebroid, but also any Lie algebroid is a particular case of a Poisson manifold, if you go to the dual. Okay? But notice that we're not talking about, of course, I'm not talking about inverse operations to go from Lie algebroids to Poisson manifolds and then Lie algebroids again. These are a little different. Okay, so maybe I'll start to talk about... Yeah, so maybe let me try to talk about quickly one more point. And then tomorrow I'll tell you the result here and a few other things. So basically what I want to talk about tomorrow is how you generalize basically the first theorem of Lie algebroids and the theorem I'm going to talk about for symplectic groupoids to the context of Poisson groupoids, and then in analogy to what we did for Lie bialgebras, which was like to find a nicer way to find them, in terms of these Manning triples. What happens if you try to do this in this setup here? And then interesting things will happen from the point of view of Poisson geometry and objects of interest. Now, okay, so let me just see how to do this. Okay, so I wrote here integration 1. That was the first integration problem. So this is another integration problem that you could state if you have a Poisson manifold. So given a Poisson manifold, you can associate to it. So let me call the Lie algebroid of a Poisson manifold. Well, let me denote it like this. Right, so it's the cotangent bundle with the Lie algebroid structure that comes from the Poisson structure. So you have, out of this, you have a Lie algebroid. So a natural integration problem is whether you can integrate this Lie algebroid to a Lie groupoid. Right? So and suppose you can. How's that related to the symplectic groupoid of the first integration problem that I stated? So this one you can state without knowing anything about Lie algebroids. And this one is a statement about Lie algebroids. What is the relation with the first integration problem? Okay, so let me try to clarify that. And the key point is this. So if you have a symplectic groupoid, with the symplectic structure, right? So as we saw, there is an induced Poisson structure on the base, right? So now you have two algebroids around. So you have first the Lie algebroid associated with the groupoid, which in principle has nothing to do with the symplectic structure. There's just a Lie algebroid there. And because I have an induced Poisson structure on the base, I have a second Lie algebroid in the picture, which is just the cotangent bundle of the base with that Lie algebroid structure. Right? So given the symplectic groupoid, I have two, in principle, Lie algebroids around. And so here's a lemma. or an observation, or actually better, an exercise. So there is a very natural map from the Lie algebroid to the cotangent bundle of the base, which is the following map. So notice that if I draw the base here, M, so here is Tm, and the Lie algebroid is transversal here, right? So Tm plus A gives the whole tangent space of the Lie group over the identity, right? This is just because the source fibers are submersions. And so what you do is this. So if you start with an element of the Lie algebroid at a point, then you contract it with the symplectic form, right? So have in mind this. So you contracted the symplectic form, so I have something that is in the dual of the tangent bundle of the Lie group at that point, and then I restrict it to Tm, just to this part. So that's the map, that's the explicit map. And the claim is that this is an isomorphism of Lie algebroids. So the fact that this is an isomorphism of vector bundles is basically comes from the fact that M sits inside G as a Lagrangian submanifold, right? This takes care of the kernel. But then to show that this in fact preserves the brackets. So here you have a Lie bracket, and here you have this Lie bracket coming from the Poisson structure. Then it's a little bit more work. And in fact, there is one formula that could be really the exercise, but that explains it directly, which is the following property of a multiplicative 2 form, or form in general, is that if you contract a multiplicative form with a right invariant vector field, then you get something that, so this holds. So if you prove this formula, which comes from the multiplicativity condition for the 2 form, then I claim that this is pretty simple. You just plug in the brackets here, just as we did before, and then the formula will come out very, very easily. Oh, I'm already over time, I guess. Okay, so let me just conclude with the theorem. This is the conclusion. So what is the conclusion from this observation here? Is that if you find a symplectic groupoid for a Poisson manifold, that is to say, if you solve the integration problem 1, then you solve integration problem 2, because the symplectic groupoid will automatically integrate this Lie algebroid. That's exactly what the exercise is saying. Now, on the other hand, and that's the more difficult part, if you integrate this Lie algebroid, so it's not even true that you can always integrate, but if you can integrate this Lie algebroid, then if you take the source simply connected integration, if you take the source simply connected groupoid that has this as a Lie algebroid, it will automatically be a symplectic groupoid. And it's not necessarily true that other integrations will have symplectic structures, but certainly the source simply connected one will. Okay? And so I'll talk more about that tomorrow, so just stop here. Thanks.